So I'm Martin Weymann. I'm the CTO of CES, Creative Electronic Systems, based in Geneva. I would like to talk to you right now about how to address the challenges of safety critical systems using COTS modules. Okay, to set the context, let's have a look at the requirements in the field of mission or safety critical avionics applications. So we're seeing more and more safety critical applications coming up, among other things because UAVs are making their way into civil airspace, which is driving up safety requirements. Now, avionics systems may be quite different in their type and requirements and functions. You may have flight control systems, you may have mission systems. Typically, these systems involve also video processing, and there are many others, each with their own specific requirements on safety. As usual, programs operate normally under high cost and time pressure, and this whole environment is quite risk averse for a very good reason. If safety is at stake, you don't want to mess around, you don't want to take any unnecessary risk. With small aircrafts, especially unmanned aircrafts right now, there is a high pressure to reduce size, weight, and power. And once you have deployed a solution, you're going to maintain it for decades. So the long life cycle in this field is also something quite characteristic. I talked already about the increasing number of unmanned avionics systems. Now, with all this, there is a need for a path which is fast, reliable, and cost-effective, also to address the challenge of safety-critical solutions. How could we do that? Obviously, if you had a set of COTS modules, this would help to reduce development time. It would help to reduce costs, and it would help to lower the risk. The challenge here is to come up with a set of COTS modules which is already designed to be safety certifiable. So one way we try to do this is we set out to design COTS modules to design assurance level C as defined by DO 178 for software and DO 254 for hardware. The idea with this is that you can reuse certification artifacts produced during the development in certifying different variants of systems which you build out of these modules. This is possible if you don't just design one module after the other, but you design a whole set which is from the start built to work together and to form a system. This takes some analysis of commonalities between different avionic functions. So typically, you may need a CPU, a processing element, which can be certified to relatively high levels. You always need some avionics I/O, like 1553 or RINC 429. You may, in many applications, need a video system with more or less safety requirements according to the application. And you may also need high-performance CPU power, but frequently for the high-performance area, the safety requirements are less important than for just control applications. For all this, you have to look from the box level, from the line replaceable unit level, and build your set of modules to leverage the advantage over there. And by intelligently choosing your set, you can cover quite a large variety of applications. And in order to define this set, obviously it helps if you already went through the process of certification in several cases from A to Z to the most highest level of safety requirements. Now, one thing, talking about life cycle, which you want to build in, is the capability to upgrade your system along the long lifetime of the project. So for instance, you may want to start out with CPU A, and sometime along the road, you would like to put in a successor CPU B, which offers higher performance at lower power dissipation. In order to do this, without having to redesign or recertify everything, it's a good idea to keep this physically separate and to mount the CPU as a mezzanine on your base card. I/Os are around for decades, so 1553 didn't change very much in the last time. CPUs have a relatively high update frequency. Now, what are the elements for success in this area? One basic principle is you have to build in safety from the start by design. It is virtually impossible to add safety requirements on an existing design later on if safety considerations have not been taken into account from the start when the design started out. Now, for instance, things you have to think about is you need to take care that your design is deterministic. We heard about this already yesterday. You have to choose your components carefully because you don't want to find out later on in the certification process that you are not able to provide or get documentation for one of your key components because it's too complex or because the manufacturer is not playing the game. You need to know which parts in your design contribute in which way to error probability. In cases where errors cannot be avoided, you need at least be able to detect them so that you can build redundant systems on a higher level. So one example for this is you take a display. If the display stalls, you want at least to be aware that the display stalled, and you don't want to rely on stale information on the display, while in reality, the aircraft is already doing different things. All this certification process passes by a huge pile of paperwork. So you have to be very careful tracing your requirements. You have to capture your requirements. You have to make sure that requirements and implementation match up. You have to trace the change of requirements which forcibly arrive during the course of the evolution of the program. And you have to build evidence for safety certification all along the road. If you take automatic tools to verify your system, you also need to have the tools qualified. So you need to prove that your tool detects an error if there is one. And to keep all this in place, you need a solid quality management on the company level. So now, given we have a set of boards to a certain certification level, what's next? In which direction do we see things evolving? So one axe of development is passing to higher DAL levels. We have requests for DAL B. This is challenging, but not impossible. In some cases, you may need to make compromises on performance, because in order to certify to a higher safety criticality level, you may want to take interconnect technology, which has been around for a longer time and which is simpler, hence easier to certify. Another issue which is on the table since quite some time and which is evolving slowly but surely is how to deal with multiprocessor SoCs in a certifiable context. So we heard about that yesterday. There are efforts like the MCFA, the multi-core for avionics, which are now slowly producing results. So we follow this closely, and we expect that in the near future, we'll have guidelines or rules for interpretation of the existing standards, which allow to handle this more intelligently than just disabling all but one core on a multi-core system. Finally, last but not least, a lot of cost-saving potential in programs rests on the fact that you can port complex applications relatively easily between different hardware platforms without redoing your certification effort completely each time. So there are several efforts addressing this question. So the Future Airborne Capability Environment phase is one of these. In the ground vehicle area, you have Victory, or the European equivalent, which is the NGVA of MILWA. So as a platform provider, you better make sure that what you provide is aligned with the guidelines and the rules set out by these standardization efforts. In conclusion, so what do we have as elements to reduce development time, cost, and risk in programs addressing safety-critical applications? We have seen that we can do this with a set of SRUs, shop-replaceable units, if safety is taken into account early on in the design process. But it's also important that you look at this from the box level, from the LRU level, and leverage the safety aspects which you have to build in the individual modules. And finally, most importantly, you have to start with safety in the beginning of the design process. So you have to take into consideration early on all the safety critical aspects of your system.